Okay,
so hi everyone. Welcome back to class.
This time I'm excited to say that we have a guest speaker, Aditi Raghunathan, who's a new assistant professor at the Computer Science Department. And she's done a lot of interesting work on academic robustness and also better understanding of some of the techniques we talked about, last time and the time before last. So I think it should be interesting maybe to give you some ideas for interesting research ideas that you're having a project on. So without further ado, I'll turn it over.
All right, thanks, Graham. Welcome, everyone. I'm probably the best pronunciation of my name, and so
I asked before, so I had training in that.
Okay. So today I wanted to talk a little bit about how do we use pre-trained models, and this is kind of a really exciting time and area because we're able to do a lot by using large pre-trained models that are available. Okay, so let me jump right in. So this is a new era in machine learning, and I guess you've been looking at it for the past few weeks. And just to get everyone on the same page, so what we're interested in is usually like the kind of models that we use today that are the most powerful are following this format here. So you train it on like divers, and it's typically unlabeled because you're just collecting it from the wild, and that allows you to collect a lot of data. So that allows you to collect a lot of data. And now everyone in machine learning knows the more data you get, the better. And so let's try to get all the data that you can. And the first step is just use this data in some manner and get a pre-trained model. And then typically big companies are going to make these pre-trained models. We're going to have these models. And then what do you do? So we want to use this model for whatever tasks you want to do with it. And that's the second step of adapting. And so, for example, you can across different domains, but you can consider many different tasks that you try to use this pre-trained model to solve. So that's the part where you specialize to a narrow distribution. So this is really a very interesting time, and a lot of it was actually spearheaded in NLP, for example, with the widespread success of BERT, where almost all NLP tasks you started using the BERT pre-trained model. It really brought in this new age of machine learning where it makes sense to train a really big model and use that in some way to improve performance across a wide suite of tasks. And in particular, this is not just something in NLP, it's really kind of finding its way in other applications like vision and robotics as well, where people are trying to build these large general purpose models that are obtained by training on large amount of data. For example, I wanted to add more, but I realized there are just too many to add. So one example that might be useful to keep in mind is the CLIP model, which is used for vision and language. And that's also kind of trained on diverse data that you get in the wild. And it really helps solve a bunch of different tasks really well. So why are we looking at pre-training? So again, there's a lot of intuitive reasons to think about why we want to do this, but I just wanted to get people on the same page here. So there's a convenience of few-shot learning. So if you have somehow taken a model that already has seen a lot of data and that's diverse, and you can use it to solve many tasks, this makes things really convenient because we don't have to go and collect a lot of training data for each new task. We can just collect a few representative examples in some manner, and now we can actually solve many different tasks. So one of the biggest complaints of machine learning before was that, well, you need to have a lot of data to do anything. But now you're saying that actually by using pre-trained models, maybe we don't even need that much data. And that's basically the few-shot learning. And not just that, it's also seen that even if you had a lot of training data, like for example, take the CFAR10 data set, which is a popular vision data set with say 50,000 training samples, and you get good performance by just training on those large number of samples. But even then, you can actually use this pre-training to further improve the performance. And I kind of wanted to stress this a little bit and say, not just can you solve more tasks, but so I study a lot of robustness, which is when you train a model, you typically don't know exactly what it's going to be faced when it's deployed. For example, you might train a self-driving car on sunny conditions, and then suddenly the weather changes, will the model still work? And that's a real problem that even if you collected a lot of data, you can't solve because you never know if your test distribution is going to be of the same distribution. But if you're actually doing pre-training, because we're not specializing to any particular task and we have trained on so much diverse data, it's really useful for robustness as well. So like you don't want to overfit to the few training samples that you got. Like you can actually use the knowledge that is in the model because it has seen so much data and get it to work well, even on a variety of different kind of distributions, which are slightly different from what you've actually collected your training data for. And in fact, like so far, this is one of the most reliable methods to actually improve robustness. So you can try to be very clever when it comes to like figuring out how to train your model. But the best and easiest thing that actually works in practice is to use pre-trained models and then adapt it to your data set. And somehow that actually preserves or like improves the robustness and makes it work across a bunch of different conditions corresponding to the same task. And just to make things a little concrete about the robustness, so let's consider a satellite remote sensing task. So in this application, what happens is you have a lot of data from particular continents, for example, North America. But the exact use case is actually when you don't have a lot of data, but you want to use it for monitoring and like do some developmental studies on like continents like Africa. So if you just do the standard machine learning, what you would do is you would collect like training data, like maybe you can collect a lot as well, but all of that is going to be from North America. And like, no, there's no reason that this is going to work well outside. And in fact, that is true that this is going to perform poorly on out of distribution data. That is, if you actually try to deploy this and do something in Africa, the model is going to do badly. So this is a real problem when it comes to trying to use machine learning models to actually do tasks which you don't have enough labeled data from already. But if you're in this transfer learning or this pre-training setting, what happens is because you've used a pre-trained model that has been trained on so much about the world and probably knows something about the different continents and knows something about general satellite images, what happens is if we can somehow preserve the information of the pre-trained model well and use it to do this particular task, now in this manner, you actually perform much better on Africa as well. So this actually allows you to use this model, like this whole machine learning setup, to work well on the same task, but from a different distribution, which captures a lot of realistic requirements that we have. And also feel free to like ask questions or at any point. Okay, so this slide should be familiar to people who paid attention in the previous class. So, how do we use pre-trained models? And this is probably a question on people's mind, right? So yes, that it makes sense we want to use, but there are so many papers out there and there are so many different settings that we could do. Like you could do fine tuning, you could do prompting, you could do like, if you go into the vision space, there's another linear probing, which I'll talk a little bit about. So there are all these things that you could do. So like, how do we actually select what to do? And that's kind of what I'll try to give some ideas or some understanding in this talk. So in the first part of the talk, we'll focus on this case where we actually have a lot of training samples. For example, like, let's say satellite remote sensing, you had a lot of data from North America, but you want to use it in a way that you can actually work well across distributions. So what's the right kind of fine tuning that we should do? And how do we make sure we make maximum use of the pre-trained model that we have? So that's the first part we'll talk about. And then we'll switch gears to looking at prompting or like this few shot setting where we don't have a lot of data and we want to somehow still use these models without actually fine tuning or changing too many things. Okay, so let's jump into the first part of the talk, which is how to fine tune pre-trained models. Basically, when you have a lot, yeah.
How do you decide which kind of pre-training method on what kind of architecture and what kind of data would have benefits on downstream tasks, like are there statistical ways or any ways?
Right. So that's a good question. And there's no easy answer to that. So usually what people find is like the more you can train on, the better. And typically people train on larger and larger amounts of data. And so the performance keep increasing. But if you were forced to like restrict your budget to like some particular, like, let's say you only could train on a model with like X samples, then the distribution matters. But what is happening now is people are just being able to train on more and more data. So you don't have to think too carefully, just put it all in and it helps. Because you can also further scale up your model size and training resources. Yeah.
Yeah, so I'm curious about like, is it possible that the pre-trained model can help us on adversarial robustness?
Adversarial robustness, not really, but like other natural distribution shifts, it does help, yeah. Okay. So how do we leverage diverse information given in pre-trained models? So in order to like understand this question, let's start from like one simple way to do that, which is let's compare two different ways of fine tuning and see if there's something interesting going on there and can we extract some general principles from that. So the two kinds of fine tuning that I'll look at is, I guess it's a bad term, but this is basically what people typically call fine tuning, which is you start with your pre-trained model. And so you get some kind of, usually you do some kind of representation learning. So there's no like real labels associated with the model. And now you want to use it for, say, a classification task. So what you'll do is you'll add a like extra of this blue layer, like the linear classification layer. And then you'll initialize with the pre-trained model for the rest of the parameters. And whatever loss you get on the training data, you'll now back propagate through the loss and through all the parameters and do it for a few steps, and still you get a good training loss. And that's how you use these pre-trained models via the most common method of fine tuning. So what you do is you initialize your model with a pre-trained model, and then basically run a few steps of gradient descent on this objective of minimizing the loss on whatever labels you currently have. Any questions? Okay, so this is usually what you would naturally do if someone told you to do fine tuning and told that you can change parameters and you had enough memory and so on. Another thing that you can do is, so this is a little bit more common in vision, because people try to think of using these pre-trained models to get representations. And if it's really a good representation, then just a linear classifier should suffice. And so this is called linear probing. So what you do is you don't touch anything that came from your pre-trained model or your representation, but you just use those representations and learn a linear classifier on top of those representations. So you learn that linear classifier based on the labeled samples that you've collected, but you don't change the rest of the features. So in fine tuning, you change everything. In linear probing, you change only the last layer, you keep everything else fixed. Okay, so as someone brought up, so there are actually a lot of moving pieces if you were trying to understand. But in this talk, like, let's only look at the adaptation procedure. So let's assume that someone has given you the model. You only have to decide how to use that model. So first, we'll look at some empirical observations that are kind of interesting, and then we'll try to see whether we can form a general story or an understanding from that. So let's compare these two methods. And this, just to summarize, fine tuning changes everything. Linear probing doesn't change everything, only the linear layer. So just to make sure everyone's awake and with me, let's do a small quiz, okay? So here's the data set. So this may be a little different from the data sets you've seen in the class, but don't worry too much of what exactly it is. Just think of this as some ML task. So you want to classify into animal categories, and the trained distribution is some subset of the ImageNet hierarchy. So basically, you want to understand, say, dogs versus cats. You've trained on some species of dogs, and you're testing on other species. Similarly, you've trained on some species of cats, and you're testing on the other species. And let's say the pre-trained model has actually seen all kinds of species of dogs and cats and everything, but it's all unlabeled. So it has seen all possible images, but it's all unlabeled. So it doesn't have any labels, but it has seen those images. And now we want to use that model to figure out cats versus dogs, but we wanted to generalize across species. Okay, so that's the task. So the first question I have is, okay, so first let's look at the in-distribution performance. By in-distribution, which is whatever species you have trained your model on and given labels, how well it does. So if you're trained from scratch, notice you do somewhat well, you get 92%. But if you initialized with your pre-trained model and did fine-tuning, you do a lot better, you get 97%. And even linear probing does well, it gets 96%. So basically both linear probing and fine-tuning, because you're using this pre-trained model that has seen a lot of these images already, somehow helps it actually improve performance in distribution. But let's see what happens out of distribution. So the first question, so how many people think that linear probing, which basically keeps a representation from the old model and just learns a linear layer, that would do better out of distribution compared to training from scratch? So most people, that's great, that is right. You do see that because this model has actually somehow seen all these other species which were not in your training data, but with labels, but it has still seen that species. So maybe it has learned something about that. And so that does help improve out of distribution. But what about fine-tuning versus linear probing? So how many people think that fine-tuning does better out of distribution compared to linear probing? Notice that in distribution, fine-tuning did better. So the question is does the same trend carry over out of distribution? So how many people think that fine-tuning does better because you've actually improved your representations quite a bit, so maybe it does better on your task? Okay, I guess it's obvious that no, the reason I'm bringing this up is yes, it doesn't. So, so you can see here that it does, so in distribution, fine-tuning did better, but out of distribution, fine-tuning actually did worse. Right, so this was kind of surprising to us because if you look at any of the vision papers, what they say is that if you could do fine-tuning, you should do fine-tuning. But if for whatever reason, if you have memory constraints or you don't want to run a lot of compute, and then maybe you should do linear probing. But like what this is saying is it's not just a notion of like computer efficiency in like ease of use, but really there's something fundamental that fine-tuning destroys some kind of robustness or some information that was there in your pre-trained model. Yeah.
Is this a function of the number of new data points that I'm tuning on? It feels like for linear probing, especially if I'm training this new layer from scratch, I would need a lot more data. It may be fine-tuning if I only have a couple of data points.
So in linear probing, you're not training from, in linear probing, you're still using the pre-trained model. So both of them are not training from scratch, just to clarify. But yes, you can ask the question of like, so what are all the factors that matter? Okay, so we'll get to that a little bit after the other example. But yes, the number of samples does matter, but really what is more important is how different in distribution and out of distribution data sets are. So to show that, we'll see this other data set. So here's another data set, CFAR 10.1. So people have probably heard of CFAR 10, where you want to classify into like some 10 object categories. So what people, researchers at Berkeley, they created a new data set, which was trying to be very close to CFAR 10 as possible, but just collected again. So what they were trying to see is even if you try to really control and like get a data set that looks very similar, how do models work? So this is different from the species case where it was very clear that there is a difference, but here we're trying to be as close, but still models typically fail, as we'll see. So I removed from scratch here because from scratch, it does like pre-training does improve and linear probing, fine-tuning, both of them. But again, let's compare linear probing and fine-tuning here. So for this data set, how many people think that linear probing will now do better out of distribution than fine-tuning? One brave soul. No one else? Okay. So the answer is no. Like for this data set, actually what happens is that fine-tuning does better than linear probing. So there's no universal answer here, and kind of to get to your point, it really depends on how close the in distribution and out of distribution are. So if your out of distribution is very close to the in distribution, then if you can improve in distribution, that appears out of distribution as well. But if there was a change, then we see that like doing fewer things actually works better. So to summarize and to like, those are just two examples, but like here's a table average over 10 data sets. So the common wisdom is that if you do fine-tuning, that's the right thing to do if you can do, especially if you have more like, all of these training data, they are quite big. And so it seems like you should do fine-tuning. And that is true in distribution, but out of distribution, the trend is reversed. And this is especially true if the distribution shift is large. So yeah, linear probing can perform better out of distribution when the pre-trained features are high quality and there are large distribution shifts. And so what this says is that there's probably a lot we can actually do to improve downstream methods. And like sometimes people might feel if all the gains that are coming is just by training bigger and better models, like what should we do? Well, actually, there's a lot of interesting questions on how do we use these models in the best way. So now let me try to see what understanding we can get, like what explains this observation. Is there something we can do such that we improve both in distribution and out of distribution, and we don't have to choose. So this is just a schematic to get at what might be happening. So let's say these are the pre-trained features. So there are two distributions here. One is blue, which is in distribution, and one is green, that is out of distribution. And remember, I said that the pre-trained features are high quality. So what that means is that the features somehow separate the X's and O's pretty well on both the distributions, but it kind of keeps them separate because there's no reason that these two distributions should be thought of as same by the representation. So what we do when we do fine-tuning is the following. So first we initialize some linear classifier or a linear head, and then we propagate gradients across the entire representation or the entire model. So what that means is that each time you take a gradient step, the features will also change to accommodate this initial linear head that you have. So in fine-tuning, the features of the examples will also change along with the linear head, because that's what happens when you propagate gradients. So what will that look like, for example, is this. So as you change your linear head, your features also start changing because you're passing gradients through the features. And at each time, the feature will try to align itself such that the linear head is good. The linear head will align itself such that the feature is good. And both of them move in tandem to reach a situation where they're well separated. Okay. So what happens is, at the end, you end up with a linear head, which is this orange line that works well on the in-distribution features, but it stops working well on the out-of-distribution features, because out-of-distribution, you didn't have any training data. And this is idealized where, like, because you're not seeing any training data, like all the gradient updates are only on the in-distribution samples. So the out-of-distribution features don't change that much. And as a result, you've ended up with having a linear classifier that works well on the in-distribution, but works really badly out of distribution. Let me pause. Yeah.
Wouldn't the green points also move?
Yes. So the thing is, the green points don't move if you have a large enough model, because there's no the parts of space that they are in, like they are actually quite different. Like these two domains can be very different. So there's no reason for the representations to keep them close, but because it has some semantic information, like it retains that information, but the features can be very far. And I'll go into that later, but we actually tested this empirically and saw how much do the features change when you do fine tuning in distribution and out of distribution. In distribution, features change by like 3 orders of magnitude more than out of distribution features. And the main reason is because you're not passing any gradients on examples that are out of distribution. Please feel free to ask, because it's kind of the core part. Yeah.
What decides what is in distribution and what is out of distribution, and by how much?
Or just the training data that you have. Like we have a train and test distribution. So for example, they could be different species, or they could be near replications. It's like how you collected your data. Yeah.
So I had 2 things. Could you repeat?
Oh, yes.
Question?
Yes. Sorry. Thanks for reminding me.
And then the second thing is, this is a really nice figure, but it's also in 2D. I wonder if there's any like ways this intuition is the same or different if we're talking about 512 dimensions.
Yeah, I think it actually becomes more true in higher dimensions, because it's like it's more obvious that some parts of the space don't affect the other. Like here, like, okay, so I guess for people on Zoom, the question that came up is, why do the green representations not change? And so in 2D, it becomes a little bit weird, like the representations don't change, but in actually higher dimensions, like all these parameters are kind of like independent and orthogonal. And so it is true that some dimensions don't interact with the other. But all we could do is like actually just like empirically verify that say the L2 distance of the change is much smaller out of distribution than in distribution. Yeah. Yeah.
So if we train from scratch, what would the picture look like?
If we train from scratch, the green and orange, like the green could be completely out of like they're not going to look anything linearly separated. It could be very complicated. So the model would actually do even worse on the green there. Yeah. Yeah.
When we do linear probing, so like won't we expect the green distribution to like change even minimal than for fine-tuning example, because we are not like really.
Yes. That's kind of getting at it. So this is only fine tuning. Now then we'll look at linear probing now. Yeah. So the question was whether features will change even less for the green examples in linear probing. The answer is yes, but it's also that the blue features won't change, right? So both of them won't change, and that's the crucial part. So that takes us to linear probing. So in linear probing, we don't change any of the features. We only learn the linear classifier. So we'll just learn this orange line. And if your pre-trained feature was good and like reasonably kept the features separated linearly, then notice that the model is now going to, like this orange line will work well on both blue and green points. None of the features have changed. So that makes sure that the correspondence between in and out of distribution still exists. Any questions? So the main difference is that in linear probing, all the features don't change. So they retain their correspondences. In fine-tuning, the features of in-distribution points change, whereas out-of-distribution points don't change. And as a result, the correspondences can be distorted or broken. You don't see that effect in distribution because the linear head changes along with the features, but you start seeing the difference out of distribution. So linear probing, the head is decent on OOD examples. But this picture also says that what could happen is, because you haven't changed your features much, your linear probing, you're like kind of forcing yourself to do as well as the representation did. So if your representation wasn't really linearly separable, for example, like these red points here, the model is going to get wrong because it can't really fit the data too well. So that's the downside of linear probing. And it kind of explains why in distribution, because you could change the features, you might end up learning a bigger separation and learn something better. But in the process, you've compromised OOD. But in the case where you actually freeze the representations, you have a downside that in distribution, you can't do better than what the representation gave you, but you don't break the correspondences, so you work well out of distribution. And just to add to Graham's question, so for example, on CFAR 10.1, like actually all the features change by roughly similar amounts. So it really depends on how far the distributions are. Yeah, so in CFAR 10.1, where ID fine-tuning still worked well, that was because the green and red were green and blue are basically very close and overlapping. So all the features change together. They're not that separated. Okay, so just based on this, like, do people have thoughts on what we could, like, one other way of saying what's happening is that fine-tuning is overfitting to your in-distribution examples, is changing things too much. And so maybe that's the issue that's going on. We need to fix that, right? So any ideas on what we could do to fix this? Sorry, can you repeat it? Yes, so people on Zoom, the suggestion was maybe we should have different learning rates for the representations and the linear head. That's a great point. And actually what we look at is an extreme version of that actually helps. Yes, any other thoughts?
Which will keep these labels not being separated too much.
Right, so regularizer that makes sure your features don't change too much. Okay, so going along that, so what those regularizers could look like is either you add some kind of a penalty to keep the features closed, or you do early stopping, like you just don't run too many gradient steps. What we see is actually that early stopping or these kind of regularization doesn't solve the problem. So the learning rate thing is slightly different, but like at least just regularizing yourself to the, yeah. So we'll get to the learning rates part later, but let's say you're like doing the normal same learning rate for both features. If you just stopped early, that is ran fewer steps, or you added a regularizer that kept you close to your pre-trained model, that does not solve the problem. So that will make it slightly better, but you still will be in a situation that linear probing works better. And this is something we observe empirically, but you can also prove in a setting. And I don't want to get into that setting, but like basically early stopping or like regularization won't fix the problem. So what will? So let's try to think through how do we get the best of both, right? So we don't want to, like, ideally, like if this model has enough information to be good in distribution and out of distribution, we should be able to get that. So how do we do that? So let's think through, why does fine-tuning do better in distribution? So the reason it did better is that whatever training data you originally had might not have been perfectly linearly separable. Your features might not be great. So what happens when you fine-tune is you like change the features and allow it to become better. So that is why fine-tuning works better in distribution compared to linear probing. But it does worse OOD because the features can now, when you start changing features, they might change a lot. But we want to dig into like, why did they change so much in the first place? And they changed a lot because your head, that you remember the orange line, was randomly initialized. So the random line was really bad. And so the features end up changing quite a bit to make sure that like random initialization works well. And they keep doing this kind of synced updates. And that was the reason. So what this is saying is that if we wanted to get the best of both, we do want the features to change, but we want the features to change only in a way that makes sense. So we want the features to change if it actually improves like the ability to solve the task, but we don't want it to simply change to accommodate whatever linear head you had initially. So we want the change to be allowed only if it's really useful, and hopefully in the process, reduce the amount of change in the features. So that's the intuition. Right, so how do we realize this? So what we suggested to do is, first, let's just do linear probing. And so we first learn this orange line. Let's do the best we can with the current features. And then let's change the features. So now when we change the features, we are not fitting a random head. We are changing the features just as necessary to like further improve on what is the best we could do. So if we do that, yeah. So if we do that in this case, we are in this situation here, where now compared to linear probing, you improve in distribution because your features are better separated, but you have not distorted them too much, and you still kind of keep the correspondence between the blue and the green. So this is also going to do well out of distribution. Any questions? Does this make sense? Yeah. Yeah, so usually it depends on like, if you fine tune it such that you like get zero loss with the linear probe, then like further updating the linear probe won't do anything. Like it's kind of already found the best pairing possible. But you can imagine like running few steps of each and integrating. I believe we tried that and it didn't do any much better than like doing one stage. Yeah. So the question was, can you interleave step 1 and step 2 iteratively? And if you run step 1 long enough and step 2 long enough, it doesn't make sense because now you've converged to a solution where the features are maximally separated for the given linear probe. So you update the linear probe, it won't change. But you could imagine running few steps of each. Actually, few steps of each might not be a good idea because one step of each is basically kind of full fine tuning. And like, so even if you do few steps, you are changing your features more than necessary. So I guess the answer is you do have to like train linear probe fully and then do the fine tuning. Yeah. And you don't want the linear probe to change too much. After the features have already changed. Yes.
Just to make sure, we don't have out of the distribution samples during the training.
No, we don't. So the reason the green lines don't change is like because that's the simplistic assumption is that the green points just never change because we don't have samples at all. So if they're very different distributions, then changing the features of one distribution doesn't affect the features of the other distribution. Yes. Yes.
So one of the earlier papers in transfer learning and NLP, what they did was they divided the fine tuning step into multiple steps. They unfreeze just a few last layers, train that, then unfreeze next few layers again and train that. What would happen?
Yeah, so you should go in the reverse direction. So you should first train the last layers and then like the layers closest to the linear head and do that. So we tried doing that. It didn't like give that much gains. So I think it's only the linear probe that is randomly initialized. All others are like kind of initialized at a reasonable value, right? So it's like whether you tune the linear head freezing everything else or not is actually what gives you the most difference. You could imagine doing it layer by layer and see some gains, but not as much because because they don't change that much anyways. Yeah.
Some intuition as to what exact problems, what kind of problems that the steps in this order will work as opposed to just.
Yes. So the nice thing is this will work for any distribution. So like you're not compromising on linear probing or fine tuning on any distribution. So the gains depend on the distribution, but you'll never do worse. Yes. So like if, for example, if fine tuning was already the right thing to do in distribution and out of distribution, like CFAR10, this will not do any worse than that. Because you're still allowing your features to change. So it kind of it's not compromising on anything in any, yeah.
Isn't there a violation if there's no pre-lunch here or something?
Well, it's not a violation because it's not like the pre-trained model is not free lunch. It's like has a lot of information. So I think that's kind of the key thing. Yeah. Yeah.
What was the question?
Sorry. Question was in general, when you like have trade-offs, like you typically are not able to like improve on both metrics. So I guess what I said is that like a pre-trained model is like actually very expensive lunch, like which someone has given you, right? So so that actually helps you in some way. Yeah. And this is actually true more generally in robustness. People sometimes claim that, you can't do better on like in distribution and out of distribution. I think a lot of it is because we don't know how to do it. But like in some sense, like we as humans can look at it and learn the right things. And so it feels like pre-trained models give you enough inductive bias to like actually be able to like do this. So, if you couldn't have done this if the green and blue didn't have any association already. So yeah. Yes.
So should there be a clear line between linear probing and fine tuning? You can do it like step by step. If you offer a little bit of the representation and step by step.
Yeah. That actually won't work. That was kind of the demonstration on the previous slide, right? So if you end up changing your features when the linear head is not perfect, you're changing it unnecessarily. So you should only change features after the linear head is converged. So that's actually the key point. Yeah, you don't want to make your features look good on like a head that is bad. Yeah. Okay, so every time I give this talk, I really cringe at the name that we came with, but this is what the paper has, so we have to go with it. So this new kind of two-step small variants. It actually, after that, we looked up papers, and there were some blog posts that recommended this, as a throwaway comment that if you do linear probing and then fine-tuning, it actually works better or something like that. So it's not like, it's not the greatest invention or something. It's like an obvious like thing that to try, but somehow it fell out of fashion because people kept doing fine-tuning because you had enough data. And so this is kind of interesting to tell you that like actually LPFT could be a good way to make sure that you are able to refine your features, but you're not doing it more than necessary. And, in this talk, I presented things, I guess I have this some experiments, but like this actually is pretty broadly applicable. For example, in RL as well, like usually people, whenever it feels like, people did only linear probing in RL pre-training because it felt like when you were also updating the features, things became very unstable. But then if you actually just fix it to say that do linear probing and then do fine tuning, then you actually improve everything. So this is like a pretty general observation, and there's actually some backing and hopefully some understanding for why this hack actually helps so much. So some experiments on at least the data sets that we considered, what we see is both in distribution and out of distribution, LPFT does better than the best. So LPFT does better than fine tuning in distribution. So, like the kind of reasoning for this is at the end of the day, you still do end up overfitting even in fine tuning if you have a lot of data, and LPFT kind of prevents that. And so even in distribution, if you just didn't have a lot of samples, LPFT will help, but out of distribution, the gain is much more evident. For example, it can improve like over 10% compared to fine tuning. So in general, if you have few data points or you care about doing well on like out of distribution samples, like thinking carefully about how you modify the pre-trained model can actually be quite relevant. This is just a table of, I guess we can ignore it since these data sets are not relevant. And so this kind of answers a few of the questions that came up. Is we did actually verify empirically that the in-distribution features change much more than out-of-distribution features if you just did normal fine-tuning. And this rough intuition is because the domains are so separate and like you have such a large model that they are in different parts of the space. So changing, updating on like one subspace or like one distribution doesn't change what happens in the other distribution. And if you did LPFT instead, then ID features don't change that much at all. So even if you actually end up with the same training loss, you can do that by changing the features by a much smaller amount by just initializing your linear head carefully. And that is great because if your ID features haven't changed that much, then ID-OD correspondence is preserved, and that actually helps with robustness or in general to prevent overfitting. Okay, any questions? Yes.
What implications does this have for multitask learning? So if you have a linear probing head for each task, then while feeding the model, then we use those heads to train the like pre-trained model. Would it address of it?
That's a good question. I guess what it tells you is in general, you want your head to be initialized as close to the task that you care about, and that will prevent forgetting. So if there's a way to do that, then that's the right thing to do. Oh, the question was, sorry, question was for multitask learning. Like, does this say anything when you try to have multiple linear heads? And what I said was like, yeah, it's at the end of the, yes, it does, because, you want your linear head to be initialized as close as possible to like being good, and only then update your features. Yeah.
I wonder if that also explains some of the success of like prompting methods.
Yes.
Because in prompting methods that have
Yes. Exactly. Yeah. Yeah. So I have that in the next slide for discussion, which is that, pre-trained models do give large improvements in accuracy, but how we fine tune them is key. And, LPFT was just like one starting point, of course. And, after that, we looked at some NLP papers and like spoke to some people, and it was kind of mentioned as a bit of a throwaway in some cases, but it is true that doing different kinds of fine tuning where you change fewer parameters, for example, in prefix tuning or these adapter modules. So I don't know if these were covered in class, but these are ways in which you kind of use your training data, but you change fewer things compared to changing everything. And these are all ways in which, similar, like they have reported similar trade-offs. So you do improve you do reduce in distribution, but you're much better out of distribution. And we'll switch gears and talk about prompting next, because the extreme of this is if you don't change any parameters at all. And that's kind of why prompting or in-context learning is a pretty interesting regime.
I think there's a chat question you made.
Oh, sorry. Okay. I don't see the chat. Yeah, maybe. Yeah, okay, I see it now. How do you initialize the linear probe here? Is it random? The key thing is you can initialize the linear probe however you want, but you can train it to convergence. So if you're just learning a linear probe, it is a convex problem. So like the initialization doesn't matter as long as you don't change the features until your linear head is learned properly. So that's what's important. Okay, so I guess the questions kind of led to the next part of the talk quite naturally, which is, can we skip fine tuning entirely? Like, let's, we spoke about all this about like, we don't want to change parameters too much, break things too much. So can we just skip this entirely? And, large language models are actually like pretty promising as a way to do that. And that's why I think it's a very interesting setting. Again, very quickly. So, large language models, as you've probably seen in your previous lectures, they're trained to predict the next token given previous tokens on like much large scale data sets. For example, and then when you train them to do this, they're good at the task of completion. So you can give a prompt and then the language model will tell you what the next likely token is. For example, if you ask the language model, Albert Einstein was a German theoretical, like the next token would be, filled to be physicist, right? So this is what large language models are trained to do. And so here's an example of what they can do. Right, so one thing is like, can we just use this to solve all the tasks, right? So if the large language model was just going to be very good at predicting the next token, then have we just solved the problem, right? Have we just solved any classification task if we just give it the right, like the sentence, if it's going to predict the next term? So it's not that simple because there are multiple completions that a language model can make, right? So suppose I want to ask a question about Albert Einstein. So let's say we're doing some classification problem and, I want to know something, Albert Einstein, I can ask some, if I just give Albert Einstein was, all possible completions are you could get physicist, you could get German, you could get genius. So like you need some way to tell the model like what exactly the task is. So that's kind of really like what happens in prompting. So yes, you have a way to like get completions, but you need to have a way to also specify what we want. Right. And so one thing you could do is, I remember I saw Graham's lecture had like, we had this feature engineering and now we're in this regime of prompt engineering, right? So you can try to like be clever and think about what prompt to do. But let's be honest, like we all don't like to think, right? We just want to give data. And so like really the gold standard would be like, let's not think about the prompt. Like, can we use data to also just tell us what the prompt is, right? So that's kind of, what everyone wants to do at the end of the day, because we don't understand how this model works. We just want data to do that. So that's a very interesting, application of this, or like this terminology of in-context learning. So what the idea is, let's not try to think too much of how we give the prompt. Let's literally just give the training data to the prompt. Right, so suppose we want to know nationalities, instead of thinking about like, maybe I should query GPT to say like, what is the nationality of X? Instead of that, let me just show a bunch of different examples and let the model figure it out, because that's usually how a lot of things work these days. And so in this way, we're not changing any parameters. We're not thinking about what parameters are optimized. We're literally just giving the the examples as a prompt. Right. So for example, let's say I was, thinking of the task of nationality. So maybe this is not a very good task because here I know what the task is and I can write it out. But in general, let's say you had a bunch of X's and labels. What you do is let's not even think about what those X's and Y's are. Let's just put them together, give them to the model and let it figure out what the task is and let it solve the task. So what that would look like is I say Mary Curie was Polish, I say Mahatma Gandhi was Indian, and then I give Albert Einstein. And now the model has enough information to know that I'm asking about nationality and correctly predict. So does this make sense, like what in context learning is? So we're not even thinking about how to give the prompt. We're literally just giving X and Y's together to the model and say, like, figure out the task and solve the task. Does this sound magical to people? Like when I first saw this, it was pretty magical to me. Like, why should this work? Like, and you can, right? Yes, right. Yeah. And like people, I mean, if you go on Twitter, you can see all these crazy examples of, like here, this is a pretty simple task. You can give very bizarre things and the model still figures out and does something. And like, for example, you can reverse addition. Like, let's say I give a bunch of examples where I use plus, but I actually do subtraction. The model suddenly learns that you're saying subtraction and does it. It's like crazy. But yeah, and so you can actually get up like state of the art on, I haven't been following too much of literature, like what state of the art, but this is what my co-author said. So you can get state of the art on like a bunch of data sets by actually just simply giving the training set as it is to the model and not changing any parameters and letting the model give its answer. Yeah.
How do you decide which examples from the training data set to provide?
Oh, don't think, just give like, give a random subset or something. Like, so you can do even the dumbest thing and it works. Yes, you can be cleverer. Like people have tried to like think about what's the order of examples and how does that matter and so on. And we'll go into that a little bit. But yes, even if you do like the most, like, as long as your context window permits, you give as many random samples, it works. Yeah.
I just have a couple of questions. So in this case, like these are very well-known figures. If we give somewhat like a newer figure, I guess.
I mean, if it's there on the internet and the data, if the model has been trained on it, like I guess the question was like, does this work on any person? And like maybe it works on more people than it should, right? So yeah.
The question was like, is this like a very fancy data? At the end, is it just retrieving patterns it has seen in some sense?
Right. The question is it just retrieving patterns that it has seen? And that's like a good question. Like, it's hard to answer that because we have no idea what the model was actually trained on. So like, we don't have complete access to what the model was trained on. But like people have tried really hard to come up with something that is like clearly not going to be in anything that the model has trained. And it still seems to work reasonably well. So I guess I missed saying a question for the Zoom people. The question was like, how do you decide which examples to give? And it turns out that like, even without being too clever, the model will do reasonably. Right. So I guess you're kind of getting at like what I was trying to get at is how do we try to understand what is happening? And like, is this something that's reliable? Can we use it? How should we use it? And like, where is this learning happening or what, like, how do we even think about what's happening here? Because it's so different from the supervised learning setting where, we actually have a model, we minimize some loss. So here we're not taking any gradient steps, nothing, right? The model is just like, you're just running the model and it gives you the answer. So this is, sort of, okay, so just to get into that a little bit more is that like, there is somewhat of a mismatch with pre-training. So if you think about it just directly, like there's nothing in your pre-training data that probably looked like a bunch of different examples of tasks with it's like, like, for example, there's no way that your pre-trained data probably had like a Marie Curie, Polish, Albert, like this kind of like, a table that it has been trained to predict on. So it's probably not seen that table exactly. And this language model is not explicitly trained to do that. It's only trained to predict the next token. Like no one told it that like maybe you have to, figure out a task from a bunch of examples and solve it. So like the model was not trained to do that, which is why it was very impressive that something like this happened. And also the prompts are not exactly formatted like natural language. Like, no one talks like, in this way, like you say a bunch of XY pairs, right? So it's not very natural. And the usually or like a large amount of the pre-training data like probably looks nothing like the kind of prompts. This is why it was kind of surprising or interesting. So I have this question, and I mean, I definitely don't give an answer to that, but like, I wanted to explain some progress that we made towards trying to like get at understanding what's happening here. So yes, so why is it hard to answer this question? Like, why can't we like efficiently research on this problem? Because real pre-training data is messy, it's huge, the models are huge, and there is also like evidence, or like most people believe that some of these capabilities only emerge at large scale. So if you like took a model with like fewer parameters and had the same training procedure like GPT-2, you don't see this behavior, and you have this so-called like emergence, which happens only at large scale. And so if you're trying to study a property that you believe only happens at large scale, like how do you even systematically study that? And so what we try to do is like, can we even come up with like some kind of a mental model to try to understand what is happening in context learning, and provide a small scale data set or a test bed. So like, can we replicate this phenomenon on like something that's like, I mean, like that you can actually like run and actually try different things? And is it actually a phenomenon of just being at scale, or can we simplify the problem in some way? And, at the end of the day, you want to use this in order for it to actually be relevant. You want to say that you want to use that to like change the way we do some kind of prompting, or like get better models in practice. So either we want better pre-trained models, or we want better prompt design by studying this. And so, yeah, so this is the kind of mental model that we came up with, and like a simple, and then a test bed that I wanted to describe. So here's the mental model. So the idea is that the way to think about pre-training is that there's already some kind of a latent concept. So each time you have a document, what you do is you first, like, there is some kind of a concept associated with the entire document, and conditioned on that concept. So once you know the concept, then you can, we say HMM because it's easy, but you can imagine that once you condition on the concept, there is some simple way of generating the data. So the idea is that there is some latent concept. For example, I guess I have the example. Yeah, so the documents are generated below. So you sample some concept. For example, you might be talking about celebrities, or you might be talking about like a particular lecture or something. So there is some concept. But then the way that concept is reflected is once you sample that concept, the rest of the text or the tokens that follow are from some HMM of the concept. So for example, let's say you have a wiki bio. So once we decide that, okay, it's actually a wiki bio, then you have an HMM that generates the actual text. So what we're saying is that if you think of pre-training as like you're like always thinking of some concept, and once you have that concept, you're generating text based on that concept, then this notion of in-context learning makes sense. And so this importance of the latent concept is like, so in this HMM, like it is like, I don't know if HMMs are covered in class, but it's a very simple model where there's no long-term dependency. But because you have this latent concept, there is actually dependency. So it is an HMM, yes, but like all of these tokens are coming from a HMM that corresponds to a particular concept. So there is a dependency. So you can't generate random text. It really depends on this concept you're talking about. And that is why you have long-term coherence in documents. And why this is a useful way of thinking about pre-training is if you just give a prompt to the model doesn't just output the next by looking at, the model has to implicitly infer what is the concept that is shared, or like where is the text coming from, and then generate its completion. So once we think about pre-training in this way, where like each document actually, or like generating the next word actually involves figuring out what was the concept that generated the rest of the text, and then generating the next word, then you can see that this is basically what in context learning, or like where that ability comes from, is like when you give a bunch of text, like the model is implicitly, when it's generation, it's trying to infer like what is it about these particular, like where are these statements coming from, what is the latent concept, and then generate it. So somehow it seems like because we have trained on diverse data, it infers concept that corresponds to simple task as well. But this is a kind of idea, or like why we think that maybe in context learning emerges, because naturally for generating data itself, we need to do this kind of inference, where suppose you have a bunch of text and you want to fill the next word, you don't just look at the word or like the words that preceded, you have to first infer like where was this concept, or like what are we trying to talk about, and then use that to figure out what the next word is, for example, looking at a few previous words. I guess my next slide says this a little more formally. So basically what happens is that the language model has to infer the concept when you give a bunch of prompts, which is what it has been trained to do. During pre-training, it always infers the concept and then generates the next word. It kind of does the same thing when it's prompting, which is kind of why it has this kind of in-context learning capability. And so if your pre-training data is diverse and it has seen, say, a bunch of different concepts, then the language model can also infer many different concepts. So the prompt distribution typically looks like, so, okay, so just kind of grounding it in what you're saying here is, so in pre-training, we said that you basically figure out some latent concept theta, and then use an HMM corresponding to that theta to generate the text. But still, if there's a slight mismatch, like at prompting, what we do is we generate, like we again pick a concept theta that can say correspond to the task of saying nationality. And then what we do is we generate independent examples and then concatenate them with delimiters. So it's not exactly the same as pre-training. So here we actually, once we sample a theta, we don't just keep generating, we generate a bunch of independent samples and concatenate them with delimiters. And so what the theory or what we show is that despite this kind of mismatch between prompting and pre-training, where in the pre-training, once we sample theta, we just kept generating, but here we generate independent samples and concatenate them, can actually prove that under mild assumptions, this, like a model that gets a prompt distribution will also output the right answer. And basically what the idea is kind of the same is each time the model gets a bunch of text, it kind of implicitly tries to imagine what was the concept that generated it, but then it tries to aggregate that over the bunch of different examples. So maybe you don't get a long sentence for each input, but you kind of implicitly aggregate over the different examples, because the model has been trained such that once you generate a concept, it keeps using the same concept. So applying the same bias, what the model will do is it'll assume that each example has the same task. So it'll aggregate over the different examples to figure out what that task is. I know I said a lot, so I'll pause here and take questions. So this is a little bit more of like a way of thinking rather than like a very concrete like algorithm or as you know a data set or something. But this is saying that the way you can think of like what's happening is that even when a model generates text on its own, it does some kind of a latent inference, and that's basically what it does in context learning as well, because it assumes that there is some concept that keeps generating everything that it has seen. And yeah, there are some nitty-gritties, like there is some mismatch, but that will actually tell us something about what prompts we should use. Yeah.
So from a supervised learning point of view, we're not doing any training
Mhm.
in context learning.
Mhm.
So these input are sort of like some information for some prior
Yes.
information to make
Yes.
the testing,
Yes.
to make the inputs more clear and concise. Right?
Yes. So basically, the saying is that if a model fits the pre-training data well, which we know large language models do, then the way they are doing that is by implicitly inferring a concept each time. And so applying that same principle to in context learning will say that it's going to figure out what the task is and solve it.
So the task information is not, it's just like some prior information to the model. Right?
Yes, the model, so the question is whether the task is prior information. Yes, the model has to be trained on something related to the task, but not necessarily the same examples. And so the model has seen this concept or the task theta in some manner, and now it figures that out from seeing small samples which are separated by a delimiter. So in the previous case, in pre-training, we don't ever take one concept and then generate a bunch of data and aggregate them. We generate a concept and then we keep generating using that concept. But what it's saying is that, even if we are not doing that, so a model that is trained to do that implicitly will say that will assume that all the examples that you've given are basically in the same concept. And that is why it's able to aggregate information over the different examples to figure out what the task is. Yeah.
Does this improve if I gave it more examples?
Yes, and in general, yes. But sometimes things like the ordering of the examples and all of that, the question is whether always in context learning improves with number of examples. In this particular theory, if with the right kind of delimiters, the answer is yes, you will always improve. But in practice, like you do run into problems like the context window, and like models somehow tend to pay more attention to the most recent tokens and all of that. So there are some, some issues with that in practice. But in general, the more samples you give, the better.
Also, say if I had to implement this for extraction instead of like a language model, like predicting the next token.
Mm-hmm.
For example, say there's an invoice and it has a total limit, and I want to give it I wanted to find the total.
Okay.
Like how would I even go about
like say doing a prompt, or is it possible to do a prompt for those kinds of situations?
Like tabular data or something like that, or like how am I?
Not necessarily the tabular data, but in general, so if I want to do it for any extraction, like from like say given the context, like I want to extract something along the lines of who is the person, like who is the author of this particular thing, it's given in the paragraph. How would I place the prompt? Because I don't know what kind of author there is or what kind of like distribution might come up in the context.
Yeah, in general, like, whatever task you want to solve, you just want to give training examples. So for example, like it feels like what you're saying is like question answering. So if you want to do question answering, what you do is you give the question, give an answer, and you give like maybe 10 questions and answers, and the model will learn to do the task. Because by seeing those 10 examples, it realizes that what you're trying to do is question answering, and that's the latent concept. And then it starts applying that concept. And so it's going to generate based on that concept, and it will give you the right answer.
One question in the chat.
Oh, okay. So if this is only a function of the data, why do we only see this happening in large scale models and not smaller models? Yes. Okay. So yeah, I guess I'll maybe proceed with the talk, and those answers will be answered, the ones on the chat. Okay. So basically, just to recap, this slide basically says what we already saw, is assuming the pre-trained language model can fit the pre-training distribution perfectly, then what it says is that to prove that this thing can work, basically involves comparing the pre-training to prompt distribution. And the point is that they're not that different except for the delimiters, or like, for example, I don't know if I want to get into this, but okay. So basically, when we're trying to do, generation of the next word, what we do is we want to find the token that maximizes the probability given the prompt that you've seen. And because of this latent concept structure, what this means is it's going to find what is the theta that was most likely to generate your y, and then generate the y according to the theta. So that is like basically you have different concepts which the model will take into consideration, and the weight of the concept, or how much the model relies on that concept, depends on how likely that concept is to have generated your prompt. So all you need is that the right prompt, the right concept should have higher probability of being generated by the prompt than any other concept. And that is really the key thing why, even though there is a mismatch in the formatting, things still work. Because yes, the model has never seen like a bunch of nationalities combined together, but given that a bunch of nationalities are given, the most likely concept is nationality. There's no other concept that is going to be as likely. So yes, it's unnatural, but all we need is that the right concept is still most likely to generate this possibly unnatural text. And that is why in context learning works, even though it's so different from the pre-training data. So the model only has to do this p theta given prompt correctly. Okay, so someone asked about empirical evidence, right? So one interesting experiment from Min et al. So this is that you can even randomize the labels in context training examples. So for example, I don't know if this is visible on the screen, but basically, let's say you're doing sentiment classification. You take your data set and you literally just give the wrong label. Okay, so each time it's positive, you call it, or sorry, you give it like random labels. Don't flip it, give random labels. Okay, so if you did this and you trained in supervised learning, like the model is going to fail completely, right? You're giving random labels. There's no reason the model will generalize. But what you find interesting is that if you gave this data set with random labels as a prompt to a large language model, the model will actually do well. And the way to think about it is based on what we've seen before, is that given these examples and random labels, if the model has to figure out what could have been the task that generated this text, even though this text is little less likely than actually the right label, the model still knows that among all possible options, it's probably doing sentiment classification. And all the model needs to do is infer that, and then it can do well. So because it already knows how to do, it already knows in the pre-training how to do this HMM of theta, like how to do sentiment classification. All it needs to do is figure out that it is sentiment classification based on the examples here, which it can do because no other task can explain what it has seen, even though it's random labels. Yeah.
It's kind of like getting right semantic field, but then the polarity one.
Yes. Yeah, exactly. But if you had actually flipped the labels, then the model can figure out that it's like actually flipping, like the theta that flips is more relevant or like more likely. So the model will flip its predictions as well. But if you give random labels, the model thinks that the true task is probably the most relevant or like most likely. Yeah.
Yeah, can we observe this evidence under a non-classification setting?
The question was, can we observe this in the non-classification setting? My honest answer is I don't know. I haven't tried or like examined that well, but maybe this paper from Min et al. Might have more information. Yes.
Just mentioned that you try to the task of say addition and subtraction, and model was able to figure out the subtraction.
Yes.
If I compare that with this example, how is it still able to?
Yes. Okay. So the question is like, okay, so maybe rather than repeating a question, I'll give the answer that makes more sense. So it's really important that here it's random, it's not flipped. So if you flip the label, then the model will start flipping its predictions. But if you give random labels, then the model will do like addition. So if you give addition with like random text or like random digits, then seeing the plus, the model thinks it's addition. So it's still the most likely thing to do. And similarly here, just seeing these words, it knows it's probably sentiment classification because nothing else can explain what you're seeing here. Okay. Yeah, so I guess maybe this already has what you asked, but yeah, so across all these different data sets, I don't know if by non-classification you meant anything more, but like multi-choice as well, apparently this shows something similar, that random, like making the labels random doesn't actually drop your accuracy very much compared to like the right labels. But having the label is important because those words actually tell the model what it is. So even if it's random, you kind of want those label information. Okay, so what other lessons can we take for prompt designing from this? So what was the role of delimiters? So the delimiters should, so the delimiters are actually ways that we put in to say that one example versus the other. And those are probably like, that's basically to break up what would have otherwise been a long sentence or long sequence generated by the language model. Now, the delimiters can either be neutral. So recall that all we want is that the model should think that the right task is most likely given the prompt. It doesn't have to be very high probability. It just has to be most likely. So the delimiters can be neutral, which means that they're equally likely for all concepts. So they don't really lean or tilt your model one way or the other. And that is fine. So most often delimiters are used as neutral, for example, like the escape characters. Or you could also try to give delimiters that are more likely that the model has seen them. So for example, the delimiters can make the model bias towards the right task. And the one way to do that is, for example, saying that nationality or like using that as like, nationality colon something is a way of telling your model that, okay, this is giving you more information that it is nationality. So such delimiters are helpful, or delimiters that just don't tell you anything at all and are neutral are also helpful, or they also work. You can have new lines and slashes, but what you want to avoid is you want to avoid bad delimiters that actually tell your model that it's probably another concept. So for example, I'm talking about nationalities, but then the examples are nationalities, but let's say I write down birth date or something, and that's going to confuse your model because now the model has two sources of clashing information about what exactly is going on. Yeah, so this is basically what I said. And so next is like, if it's really, I guess this is exactly the question that was asked on the chat, which is if it's only a function of data, then can we actually observe this in smaller scale as well? So what we do is, yes, if we reduce the token size, then the amount of data will also scale down, or like the complexity also reduces. And so like, can we like replicate this in context learning in like a much smaller scale data set? And so we tried to do that and created this like JINC data set, which is a small scale data set for studying in context learning. And so this is like much smaller scale, only retrains on like 1,000 documents, and the data is generated according to the distribution we saw before, where you sample a concept theta and then you generate from an HMM. And so this is just like nonsense tokens, but it's like a smaller set of tokens, and we only pre-train on 1,000 documents, and we prompt with a bunch of different settings, and like we concatenate, we do the usual in context learning and see whether this works. And so what we find is actually that in context learning also emerges in JINC, which means that, so K is basically the length of the example. So let's not worry too much about K for now. So what we say is across different model architectures, in context learning still emerges. And this is because the main effect is coming from the pre-training data, which is kind of what we said. We didn't try to think about which model is learning in what way. We just tell that if a model fits the data, it should work well. And so we do observe that. So, it's not transformers that were actually key. So like in small scale, LSTMs are also able to fit the data well, which means that they're also able to exhibit in context learning. So it's not anything that specific to the bias of a transformer that leads to this behavior. It's possible that transformers bias helps to fit more complex pre-training distributions well, which is why they exhibit these things. But that's about fitting the data and less about the bias of the models. Someone asked sensitivity to example ordering. And so this is something we don't have a very good explanation of, but so a paper in 2021 said that the accuracy can vary between 50 to 90 depending on the example order. And we just tried it on the Jing data set as well. And we see that basically based on the ordering of the data set, like, we replicate this we mirrored this in Jing as well, but our theory doesn't exactly yet, we didn't think about whether this comes or whether you can prove something like this, but we observed that as well in small scale. And then the other thing is extra, yeah. Oh, sorry. Yeah. Yes. Yes, exactly. So there is I think that, yeah, in the theory, the assumption we make is that you are perfectly fitting your pre-training distribution, which is probably not what happens in practice. Like you're never going to train to perfection. So I think once you're slightly off, maybe the example ordering starts mattering. And so we didn't think too much about that.
And the invariance of order comes because each in-context sample is taken independently.
Yes, yes, yes. Yeah.
I have a follow-up. So we know that transformers or neural models have a recency bias, and I wonder if the most recent example having a higher conditional probability of a different concept would be one reason why.
Yes, so I guess if you assume that there there is. Okay, so the example, actually I changed my answer. So the example order doesn't matter in the limit of infinity. So if you have as the number of in-context samples goes to infinity, you're going to infer the right task and the example ordering doesn't matter. But when you have finite samples, we don't have a way to say, because now you actually haven't figured out the right concept. And so maybe your model is going to, for example, in this HMM kind of thing. So it's even if it has gotten the wrong concept, it's going to generate looking at what it has seen previously. So in the context of infinite data, only when the ordering doesn't matter. So I take that back, yes. So you could have errors in how you actually estimate your concept, and you might pay more attention because of this HMM structure. You pay more attention to what you've already seen currently at the end. Yeah. And then finally, extrapolation to unseen tasks. So in the previous stuff, we assumed that whatever you're testing the model on were things that were seen during pre-training. And in practice, it has been observed that, you can give random things beat and sport, some, crazy association, and the test input and predictions, the model will still do it, right? And so this is not really a task that the model should have ever seen. And we just try this in Jing as well. We even though our theory is limited to pre-training, the concept seen during pre-training, somehow the model, is able to do random unseen concepts as well. Of course, not as well. So you don't get very high accuracy, but it's still higher than random. And so somehow the model is also, again, in this case as well, able to generalize across some notions. So, take this a little bit with a grain of salt, because it depends on how unseen concepts are defined, but it's not like the model completely breaks. So yeah, and so kind of the idea is that maybe if you have somehow the latent variables themselves have structure, and so it's able to actually generalize across different tasks if it has learned in some particular simple way. But yeah, this is something we don't really fully understand, but it seems even in simple cases we see that. Finally, I think what is particularly interesting is that even on this small data set, we do observe an effect of model scaling. So the in-context learning accuracy actually increases as you increase the number of parameters. And in the theory, we say that it only depends on the pre-training loss. So it only depends on whether they're able to fit the data well. And so even if the pre-training loss is the same, what we see is that larger models do better than smaller models for in-context learning. And this is something that kind of says that, yes, like maybe we can try to sweep under the rug that it's all the data, but actually that's not, there is still more going on. There is still some magic in that, like larger models are like doing better, even though it seems like they're fitting the pre-training distribution just as well. And yeah, so I guess my hunch is that, this is because the pre-training loss is not zero. Like if you actually somehow are able to fit it perfectly, then the model size doesn't matter. But when you're in that regime where you're close to perfect, larger models are somehow doing something better. And there's something about the bias of these models that we don't really understand. And like maybe this is something like, this small scale setting could be interesting to study that. So yeah, so I kind of wanted to say that like we're not saying we should just not think about the models as well, because clearly they matter. And finally, like number of examples came up. Like one weird thing is sometimes 0 shot is better than 1 shot. So sometimes saying what you want is better than like giving one example. And that's something again we see for some reason in like the small scale data set as well. We don't have very good understanding of why this is true again. But empirically, it is true that like maybe again this is some quirkiness of the models. But like somehow when you give one example, they do worse and then they catch up. Again, we don't like fully understand these, but I guess what this is saying is that this is probably a small scale test bed that actually shows a lot of the interesting quirks that we see in like the large scale settings as well. So maybe this is worth studying. And this is great because now you can quickly try out different prompting strategies. But most importantly, you can also, you can afford to do pre-training too, because it's a small scale. So you can try different pre-training methods as well. And GPT-3, for example, or any of the large language models today, they were not trained keeping in context learning in mind. It just happened. But maybe we can train to enable something like that. And the reason we want to do that is because, as we saw in the previous part, figuring out how to adapt or fine tune is tricky. So if we can have a model that somehow does it on its own, that's great. But maybe we can pre-train a model keeping that in mind. And this could be a useful test bed. The last 2 minutes to this summarize everything. So pre-trained models need to be adapted in some way. And we kind of, we want naive adaptation can be bad because we change more than we want and we kind of risk overfitting and losing information from the pre-training. And simple changes can actually fix these problems. And like one example was LPFT, but there's probably a ton of things, and especially in NLP, like given the various kinds of prompting that we have, there's probably a lot of interesting questions here. And then the question is like, can we, figure out the model to automatically adapt, and in context learning gets at that, and it's very surprising.